Hi, in this video, I am going to introduce you to a little bit of circuit engineering or circuit design. Maybe I'll call it engineering because it's fun for me to imagine that students in this class might be aimed towards becoming engineers. You could be circuit engineers, or you could be an engineer that simply needs to design a circuit so that you can cause some other piece of technology to get advanced, right? Yeah. Also, even just people who are electricians, right? So you might have a job where you go and you rewire a house, and you have to do this safely. And you actually also have to do it taking advantage of advantages in certain circuit designs versus others. Okay, so essentially, right, building a circuit, like a simple circuit, one battery, say one light bulb and some wires, you can use the battery to turn the light bulb on, right, deliver energy to the light bulb. And as the light bulb uses that energy and sprays it out, that battery is losing its energy. If the light bulb could be caused to be brighter, then that means that that battery is losing its energy faster, right? Because energy is emitted by the light bulb quicker. Okay, so but there can be many different types of circuit shapes, right? Depending on how many batteries you're going to put into your circuit, right? Maybe you want to use 2 batteries or 3 batteries because there are various advantages to making that choice. Also, maybe you want multiple light bulbs lit up, like for example, like a string of lights above a picnic patio for summertime dinners out in the backyard. And of course, you can use a bunch of different wires. For circuits, you tend to need at least a wire. And if you have complicated circuit shapes, you might need lots of wires, 10 wires, 20 wires, right? Okay, so yeah, the short of it is there are many different ways to hook things together to make various different kinds of circuits. And some of the most basic ways or choices for different ways are the choice of making 2 things in parallel or making them in series. So what this means, for example, in the case of parallel, this kind of shape for a circuit is the situation where you might have a wire and there's an electron on the wire moving down the wire towards the right. And in the parallel case, the electron is going to find itself at a place where it can do one of 2 different things, and it cannot do both at the same time, right? So for example, in this particular case, here's a light bulb, and here's another light bulb, right? This electron can either go up to the upper and through, right, to become over here, or it can go through the lower and keep on going through there. So these 2 light bulbs are considered in parallel because an individual electron can only do one and not the other, right? So that's what's meant by parallel. This is sort of similar to leaving a grocery store. When you leave the grocery store, if you have multiple clerks at the cash registers, then as you come up, you can either go through cash register number 1 or cash register number 2 or cash register number 3. And these groceries tend to have cash registers in parallel because it tends to speed up shoppers' shopping experiences, which shoppers like, and they tend to come back if they have lots of options on going through checkout stands, right? So what shoppers do not do is go through cash register number 1 and then go through cash register number 2. That, of course, is not true if something goes wrong at cash register number 1 and you have to sort of repeat the process. But that's not the case in circuits, right? An electron, as it comes along and has a viable circuit option, so here the option starts right here, right? And it can go up or it can go down, but it cannot do both. This is in contrast to the series case. So in the series case, here's a wire, and along the wire is a light bulb. And after light bulb number 1, there is another light bulb number 2. And if you consider an electron that has to go towards the right, it's going to first go through number 1 and then through number 2, and then it's just going to keep on going, right? So the current is flowing towards the right, and each electron in the current must go through one light bulb first, and then it cannot skip the second light bulb. It must also go through it because the electron is confined to the wire, and if it moves along the wire, then it moves through light bulb 1 and then light bulb 2, right? Compare against the upper case, the parallel case, right? The parallel case is this electron has a choice. And once it ends up making one of the choices, right, if it goes through the upper light bulb, it cannot go through the lower light bulb. That option is no longer available to it on this one pass. But in a circuit, it's going to come around again, and it might elect to go through the other one, or it might go through the one that it went through before. But each time around, that choice is random. Okay, so I'm showing you the cases of light bulbs in parallel. Oops, I put parallel in the wrong place. This is actually the series combination. So these are light bulbs in series. And up here, these are light bulbs in parallel. Right? But the light bulbs, right, aren't the only thing that can be in series and parallel. Batteries, the power supplies, right, the energy storehouses can also be in series and parallel. So let's put 2 batteries in series. So what happens is if you do this, right, so let's put this battery this way. So I put the positive terminal on the right side, the negative terminal on the left side, and I'm going to connect it by a wire to this battery, oriented the same way, plus on the right, minus on the left. And these 2 batteries in series, I'm going to hook them up to run a light bulb. So I used a couple of wires to connect these batteries, which are in series, to a single light bulb. So the interesting thing is if this is a 1.5 volt battery, and this is a 1.5 volt battery, this situation is actually equivalent to using a single battery, plus on the right, minus on the left, that is 3 volts. When you put batteries in series, the voltages, they add, right? And so when I finish the circuit with the light bulb, this light bulb is being driven by 3 volts and is very, very bright, right? And if you put more batteries in series, you could make a 4.5 volt battery with 3 batteries in series. You could make a 6-volt battery with 4 1.5-volt batteries in series. You'll just get brighter and brighter light bulbs because, remember from Ohm's law, the thing you are not changing is the resistance of the light bulb. It's always the same light bulb. But what you're causing to happen is you are using bigger and bigger voltages. So in terms of Ohm's law, the current equals V over R, and putting batteries in series makes the voltages bigger and bigger and bigger. And so that results in bigger and bigger currents because you have bigger and bigger voltages and this very same light bulb, the same resistance. So big current is a fast delivery of energy to the light bulb, which means the light bulb is spitting out that energy quickly, and that is called bright. That's called brighter. Okay, so advantages. If you put batteries in series, then the advantage is you get a very strong voltage that can push a larger current. But a disadvantage is the fact that these batteries run out of energy quicker. And that's because the light bulb is bright, right? So the bright light bulb indicates the fact that energy is being sent to the light bulb from the battery quicker. Yeah. So that's a disadvantage. Let's consider batteries not in series, but what if we put 2 batteries in parallel? So how will that look? Here's a battery, plus, minus. Let's say it's still 1.5-volt batteries. Here's another battery. And I'm aiming to put them in parallel. So what I did was I drew them in parallel, right? I just made a drawing of them in parallel, kind of like the light bulb drawing. Can you see that these 2 light bulbs are in parallel? They're drawn next to each other, not in series. Like these 2 batteries here, those are in series. So here's a couple of batteries. I drew them in parallel, but I did not hook them up. So the way I hook them up in parallel is I do the following thing. I'm going to take a wire from the positive ends of both and connect them to each other with some sort of a weld or a touching connection, just a conductive connection. It's kind of like 2 wires merge into one. And I'm also going to make another connection on the backside that looks just the same. 2 wires merge into one. And now these 2 batteries are in parallel. And if I hook them up to a light bulb, there it is. What's interesting about this light bulb is it's not going to burn very bright. It's going to burn about half as bright as this case where I used the 2 batteries in series. So I'm going to draw it looking a little bit dimmer. Can you see that the shining light seems to be less? This is very bright. And down here, this is a little bit dimmer. And the reason that it's dimmer is because the current is not very much. In fact, actually, the current that flows through this light bulb is equal to 1.5 volts. So even though I've got 2 batteries working together in series, the overall voltage is still only 1.5 volts. And then the circuit resistance is the same resistance for the light bulb, which indicates a somewhat small current. What's interesting about this, though, is the current that's flowing, right? The electrons are moving towards the left in this battery and towards the left in this battery. So they are going this way along that wire and this way along that wire. they merge together and make the current I. And so this is sort of like rivers. You can have half the current flow on one stream and half the current flow on the other stream. And when those two streams merge together to make the bigger river, that current flow is I over 2 plus I over 2. And that current flow goes all the way over here, so it's a full I. But when it gets to here, the current flow splits in half again. I over 2 and I over 2 down this way. Right? So the current flowing through this battery is I over 2, and the current flowing through this battery is I over 2. But the current flowing through the light bulb is all of I. So the current has split. The advantage of this is even though your light bulb is dimmer, this has a working light bulb for a long time. And it's because the batteries aren't being used as quickly. They're not having to deliver, so each battery doesn't have to deliver as much energy to the light bulb, right? So they're working together in the sense that they are both working slower to provide the same energy as if we were just using one battery to power the light bulb. Yeah, it just lasts twice as long. Okay, so that would be considered an advantage. A disadvantage is when you use the batteries in parallel, the voltages don't add together. I don't get 3 volts. What I get is still 1.5 volts, but I just get to use this circuit for much, much longer. It's going to work for a longer amount of time. And if you think about it, it's just an energy conservation thing. If you don't use the energy quickly, then that device lasts a long time, right? Because you don't get to have energy for free. But if you use the energy very quickly, then that device might work really well for a short amount of time, but after that, there's no more energy to use. Okay, so that was talking about circuit shapes for batteries. But what about shapes for loads, right, which are also called resistances? So let's take a battery and consider putting 2 light bulbs in series. So I'm going to connect this battery, minus plus, right, to this light bulb here. And the electron that's being pushed along by this battery, right, is pushed from the left towards the right through this light bulb. And then afterwards, it goes through this light bulb. If you look really, really close at a light bulb, let me show you what it looks like. So this is a cartoon drawing. It's kind of like a tube. The wire itself is a tube, right? And this thing gets really, really hot. And when it's hot, right, hot things glow, right? When you put a piece of metal in the fire for a long time and the temperature of the metal gets really, really warm, what it does is it glows. And that's how these old light bulbs worked. So they get hot and they glow with the light. That's how they behave as a light bulb. They're also really hot to the touch, right? So when something gets really hot, there can be thermal expansion. That is, the shape of this thing can change. Also, when you make it hot, then cold because you turn the light out, and then you turn the light back on and it becomes hot again, and then you turn it out, it's cold. This is called heat cycling. Heat cycling can cause changes to the filament or the wire that causes the wire to become more brittle. And so as you heat cycle it and it becomes more and more brittle, what can happen is there can be, a place that becomes broken, right? And so the idea is the circuit actually breaks. And so let me see. So what I mean by that is in between here and here where it got really brittle, the wire actually breaks. So there are raw ends. So if I go and I draw that inside of here, so there's that little raw end, right? So this is an open circuit. And if it's an open circuit, current won't flow. So current will stop. And if the current stops, then that means that the battery no longer delivers energy to the rest of the circuit. So not only does this light bulb turn off, this light bulb also turns off. And it's because the current turns off. And the electrons just stand still again. Okay, so this is a danger of putting light bulbs in series. It's not really a danger, right? The light bulb can wear out and break like it did over here. But what if you put light bulbs in parallel instead? So let's contrast that. So here is a power supply or a battery. Here's the positive end and the minus end. And I'm going to put two light bulbs in parallel. So the way I do that is I use a wire that actually has two ends to it. Can you see I just changed the shape of the wire? And on this end of the wire, I put a light bulb. And on this end of the wire, I put a light bulb. And you can see that I put these two light bulbs in parallel. And then on this side, I'll make a similarly shaped piece of metal, right, which is just a wire. Make sure that the metal is all connected. So there's conductivity at all the connections. And then when I run this scenario now, this light bulb turns on and this light bulb turns on. And the reason is because this light bulb is getting a current to pass through it. Let's say it's the current I. And this light bulb is also getting a current passing through it because this is a complete circuit and this is a complete circuit. So both are going to work and both are driven by the same battery, the 1.5 volt battery. So an interesting thing to wonder is what if one of the light bulbs turns off for some reason? I'm going to say that it turns off because the filament inside broke. Right? So you can see that there is an open connection there. So what happens is the current right here is going to shut off because this is no longer a complete circuit, right? It's not complete because of the broken filament. So that current has to go away. So let me erase it. Get rid of that current and this current. I'll get rid of so the light bulb turns off. But the lower light bulb continues to burn actually. And the reason is because there is still a complete cycle here. This 1.5 volt battery is connected across the ends of this light bulb. So this 1.5 volts can push current through this light bulb here, right? And that light bulb stays on, even though this light bulb turned off. And that would be considered an advantage of putting light bulbs in parallel. A disadvantage of putting light bulbs in parallel comes up here. So here's another battery, and I'm going to be a little bit crazy and put a whole bunch of light bulbs in parallel. So here's a light bulb, here's a light bulb, here's a light bulb, light bulb, light bulb, light bulb. So this looks like 1, 2, 3, 4, 5, 6 bulbs being powered in parallel by this 1.5 volt battery. So the issue that arises is the following, and this is why this situation is dangerous. Let's say that the current I is traveling through this light bulb, causing this light bulb to burn with this brightness. And because the circuit is such that the current can also go through here, this light bulb is also going to turn on at the same time, also have the current I through it. And so is this light bulb, and this light bulb, and this light bulb, and this light bulb. It's interesting that even though this light bulb down here is the furthest away, it's still just as bright as the light bulb closest to the battery. So they're all the same brightness. They all carry the same current. But the reason that this is dangerous is because look at what happens as the currents rejoin to make the river. So this current joins this current, and so along this wire right here is a current that's 2 times I, right? Because each of these individual I's merge back together and make 2I. But when this I joins it, now the current flow is 3I. And when this current joins it, now it's 4I. And when this current joins it, it's 5I. And when this current joins it, it's 6I. When currents are really, really large, this can lead to a problem of hot wiring. And actually, let me, that's a bad way to say that. Hot wire is like something different. This is the situation where wires carry too much current. What this leads to is the wires themselves become hot, and when the plastic coating around the wire gets hot, it might light on fire. And so this becomes a fire hazard, right? So this kind of situation here where you put all these things in parallel, right? You could have a toaster, a hairdryer, microwave, your television set, right? You're charging your computer. All of these things are happening at the same time, and the wires closest to where the sort of power company delivers your house power, those wires might be carrying too much electricity, and they get too hot, and that can cause a fire. And that's the sense in which this could be dangerous. But the reason that it's also useful is because if any one of these 6 light bulbs was to burn out, the other 5 light bulbs would continue to operate as normal.